So the notes I sent you had to do with motion in one dimension. And I want to say from the start that um, motion in reality is so complex, very, very complex, that we cannot jump straight to analyzing motion in the real world so easily. We have to start with the very basics, and here's where we want to start. We're talking about motion in one dimension. What do I mean here? Sometimes you hear the term motion in a straight line. Motion in a straight line, right? And that's what we're talking about. A body moving in a straight line, right? They're either going that way or they're going that way or they're, moving to and fro, right? Um, you see the motion like this if you were to throw up something vertically as well, and it falls down back in the same path, right? Maybe if you have ever dropped a ball from a height, or it's very difficult, but you can throw a ball up, or you can throw an object. I'm saying ball. You can throw an object either vertically up, right? Or you can drop it and let it fall vertically down. So for us to analyze motion, we have to start with the simplest of them, right? We're going to start with one dimension. As a matter of fact, your course does not get into even motion in two dimension. Two dimension is like, okay, you're throwing something. I don't know if any one of you ever, you throw a ball or you throw an object. So what's happening? It's going up as well as it's traveling this way. This is motion in two dimensions, which is a little more complex. As a matter of fact, we can go further and deal with motion in three dimensions, which is very, very complex. For the boys who, anybody following cricket and so, or well, we don't follow baseball in Guyana, but cricket. So those of you who
Yes, sir.
watch these guys bowl, especially the bowlers who do what we call spin bowling, right? Um, you hear about off break and leg break. Anybody can say what that is? Anybody knows what that is? Anyone of the boys? Nobody know what is off break and leg break?
Sir, not only boys watch cricket,
Yeah, well,
but
tell me if you watch some cricket. Tell me what you we ever heard those terms?
yes, sir. Sir is like when you spin the ball. Well, the
Uh-huh.
spin bowler deliver and is from the offside from the forward leg. So sometimes you might hear this a water band bowler yaka there, you know.
Okay. Yeah, Yorker is a different one too. Yeah,
It
bowlers
is,
might
but you
not
know,
just bowl. Okay. Um, they might not just bowl. Okay, the ball goes up, right, and then goes forward. There's a third dimension where the ball can move at an angle to this horizontal, right? Uh, Especially you see in cricket, the ball usually bounces and then the batsman hit it, right? And it is on the bounce that you have the off break or the leg break, based on how they hold the ball and release it, right? But in this game they call baseball, right? Where the ball doesn't bounce on the ground, you bowl straight. Well, the idea is that you want the batsman or the hitter, right, to miss the ball. But sometimes you bowl it in a way that okay, not only goes up and then come down back and goes towards the batsman, but they also bowl it at an angle, what you call a curve ball. You ever heard that statement? They make a movie named Curve Ball. A curve ball. That's three dimensions of movement. It's going up a little and then coming on back. That's one dimension. Up and down is one dimension. right? It's going towards the batsman, which is another dimension. And then there might be a curvature, right? I can't really show three-dimensional motion here, but I'll just, let me maybe attempt to. So from if you were to watch sideways, right? You're watching sideways. The ball goes up and towards the person hitting it, right? So there's two dimensions involved, this one and that one, right? Up and down, right? In this case, it's going forward. It's not going to go back, right? But then if you were to watch from the top, the ball might very well go like this, right? Not, I mean, I exaggerated the curve. So the pitcher is here, right? And the batsman is here,
Sir,
right? So
this
when you
often
watch
be
from the
used in
top,
football as well. In soccer, they
yes,
would usually curve the ball when they kick.
very good. Yes, if you kick the ball and maybe you kick it in such a way, you know, the way you kick this ball, which part of it you kick and whatnot, the ball could very well go in a curve. So when the goalie is here and he thinks the ball is going to go straight, no, the ball goes that way. But then he reaches there, he misses it, right? I'm looking from above here. So I mean, I'm telling you all of this, but we are not going to be dealing with that complex motion, right? The reason why is that the physics and the mathematics um, involved is very complex. And it's for you, if any one of you ever have to, or I mean, if you decide to switch your studies and that sort of thing and choose to study either physics mostly, right? And you go to that extent, you'll study mechanics 1, mechanics 2, right? And you will, well, mechanics 1 actually we do cover motion in 2 dimensions. And then if you were to do mechanics 2, well, then you get into motion in 3 dimensions, right? Which is rather complex, right? And an understanding of that can, you know, really do well for you. I'll tell you why. I know I'm dealing with one motion, 1 dimension. Why am I talking about that? But I just want to tell you the potential. Y'all ever watch cricket and you see they do something called ball tracking, and they have this computer program that will tell you that if the man bowl the ball with this speed and the ball, well, they know how the ball is released, right? And how the ball is going. They can tell you if you're going to hit the wicket or not. You notice that going on?
Yes, sir.
Yes, sir.
And you would notice that some matches have it and some matches don't have it. Some matches would have a simplified version of it, where all you see is like a shaded region where the wicket is straight to the bowler. And then they will make up educated guess as to that the ball will hit the wicket. Others are more complicated, where they show you the flight path. And then they'll show you when it hits the ground, whether it's going to go on to hit the wicket, which stump is going to hit, whether it's going to miss. You notice that, right? But you all don't realize that what has happened there. It could be a person or a team of persons came up with this computer program that can take all these inputs and analyze the motion in 3 dimensions. Now, one dimension can't work there, not even 2. All 3 dimensions, right? And they can tell you whether the ball will hit or not. Sometimes you ever wonder how do they know that? And as a matter of fact, when they have a tournament, whether be it like the recently concluded World Cup, and if they want ball tracking, right, they have to go to these people who own that software, and they'll sit with them and say, man, you know, World Cup is coming up, and we want to license the software to use for if it's 3 months or how much. And then the ball tracking team is going to say, all right, how many matches you need it for? And we can get technical people on the ground and blah, blah, blah. All right, yeah, that would be $1 million. You understand? So as stupid as it sounds, these men who came up with ball tracking can now make that kind of money just because they understand the mathematics right? And the physics behind it, and they could take it over to the computer and create this software that now is so useful, right? And who knows, they also, if it's not them, some other people, they have a program that the baseballers, people who play baseball, right? They would also license the software to use for tournaments and so, or games, and they make millions of dollars, right? So understanding these things is it can mean a lot for people, right? It's just that we just a lot of times we see everything we learn in school, we think that man just want us to learn this thing and for waste time. And other people see it different and say, you know what? Why don't we turn it into something that is useful? Right? Look, just I'm deviating again, but I just want to show you how sometimes when you look at things, right? You want to think of how you could, do something practical with it. Watch. Even that same cricket, you all see that thing long ago, they used to have some wooden bales. What do you see now? You see, they call it zinger bales, right? You all see them? When the ball displaced the bales, the bales light up. Do you see that? The wickets and so light up.
Yes, sir.
Good. And then you see some games they don't have it. They still have some wooden sticks with some wooden bales. Some games would have it, some games wouldn't have it. Right? And again, how you think that happens? Somebody came up with the idea, you know what? Man, you're never too sure the umpire now see good, we up here don't see good. Could we come up with a way that will tell the whole world that that bale has been dislodged? And they say, look, especially nighttime, right? With the advent of 2020 cricket and night cricket and white ball cricket. And then somebody says, let me design something. And they design something that when the circuit is broken, right? When it's open, well, I'm wrong to say the circuit is open. When the ball, when the bale is dislodged from the wicket, a circuit is actually closed and a light comes on, right? So whether they use motion sensors and whatever else they use, right? The point is somebody took it, and now again, as I told you, when ICC ready to do the World Cup now, or when we are going to they're going to have IPL and CPL is going to go on soon, you have to approach these people who own the technology, right? I said, man, I want to. We're going to do CPL, and we need to license your technology. People say, huh? Okay, all right. Yeah, I meet my sales team, and the people say, all right, y'all gotta pay us $1 million US. Money. You understand? It's $2 million. And I ain't joking when you hear them figures that. You think they'll give it for 100,000 US? No, I might very well say, depending on the size of the tournament. Like IPL, they have to pay more. For CPL, it might be a smaller thing, Because IPL, I think, is 60 something, 70 something matches. CPL is just about 30 or so, right? 30 something matches. So I'm just showing you how, these things, understanding the basics and building on it, and you can harness it for greater things, right? Of course, we are not concerned with that in the course. We're concerned more with how we can move towards safety and well-being, in particular in the workplace and even in the homes and your everyday environment. That's what we're concerned with. But it doesn't hurt, as I said. You take something and you build on it, right? Good. So now that we clarified when we talk about one dimension, we talk about in a straight line, right? You're going in one direction. Good. I did talk about some terms earlier. I think another day we talked about the quantity of distance, and we distinguished it from displacement, right? So we're saying that displacement is really a distance in a specified direction, right? And we illustrated with maybe, okay, you're walking from there to there, and oh my, what is happening here? Why are they interpreting my motion with something else? Yeah. So maybe you walk that distance there, and then you walk another distance here. And These are two distances. You can write them as displacement. You can say that this is maybe all right, 10 meters north. You can write this distance. You can qualify it and make it into a displacement, right? And you can say, all right, this is 15 meters east. You can call it that, right? But for the sake of explaining what distance means as against displacement, I think I said distance here would be, okay, this 10 and this 15, right? Which will give you 25 meters. That's the distance you travel if you were to move from here to here. Maybe this is the path, right? But your displacement from the original position here to here, right, is this shortest distance here, right? And you can use Pythagoras theorem to get it, and so, and you can even add on a little dimension of direction. You can add that other property, right? So displacement carries both magnitude and direction, right? So we want to go a little further. Oh, by the way, the beautiful thing about when we are dealing with one dimension is that distance and displacement can be used sometimes, not every time, because we can very well treat a motion like this, right? Because in this motion from here to here, you didn't stick to a straight line. You went on a straight line here, and then you changed direction and you went on a straight line, right? There are other times when the straight line, okay, it's the entire journey is on a straight line. When that happens, the two words, displacement and distance, can be used interchangeably because there was no change in direction for the entire journey. So if you're moving from here to here and it's a straight line, which, I mean, again, in practical or in reality, you don't have very, you don't see this often where, the path someone takes is straight all the time, right? There's always a change of direction all the time, right? But whenever that happens, and when we're dealing with motion in one direction, if you're dealing with a portion of the motion of a body, and you're dealing with one straight line, distance displacement sometimes can be used interchangeably, right? In this scenario here, while indeed the distance is in a straight line, then you change direction, go this way. You might not be able to use distance and displacement interchangeably, right? So keep that in mind. So sometimes they could be used interchangeably, sometimes they you just cannot, right? Especially when you're dealing with a change of direction, like maybe you're driving. Let's say this is the road, right? This is not a straight line, so here displacement and distance will mean two different things, right? They won't mean two different things. Good. Let's go. Well, we did say that your distance can either be in meters. If it's a longer distance, you use km. We're gonna stick with these two, right? We're gonna stick with these two. Maybe if you're dealing with something where, maybe it's some small object, maybe more on an experimental level, and something moves, in a short distance, and we can use centimeters, but most of the time we'll be using meters and km, right? Because these here, you see these more in the situations we encounter in real life, right? And I guess by now you know to change from meters to km, and from km to meters, right? Everybody can do that?
No, sir.
No, sir.
Sir, with a calculator.
No, sir.
Multiply and divide.
Exactly. By what? By what? Somebody said the right thing. It
With
I
a
believe it's a
calculator.
I mean, the calculator isn't intelligent. It doesn't know what to multiply and divide by. If you ask the internet, maybe you have an AI, or you ask the internet, they will do it for you. But a calculator, you'd have to know, how do you convert meters to km? What do you do?
Divided by 1000.
Sorry, the multiply
Great.
and divide.
That person said it. To change from meters to km, right? you divide by 1,000. To change from km to meters, you will
Multiply.
multiply by
1,000.
very
1,000.
good. Yes, keep that in mind, right? And as I mentioned before, when we were doing the units and so, right, the SI units, for some reason, right, we can divorce ourselves. Is who sing the song? Is this Bob Marley sing a song about our emancipating ourselves?
Yes, sir.
I don't know the song, but I remember there was this thing about slavery done, yes, and indentureship and so done. But let me tell you, we can't shake England off ourselves, and people still in this day and age, people still talk about miles, right? And we simply can't get rid of it for some reason, right? I don't know what they do to us. But miles, how much a mile is a km roughly? Maybe just give us a rough something. Anybody knows how much km is a mile, or let me put it that way. I'm looking at the
Sir,
internet here.
1.609.
1.6.
Yes, I'm seeing that on the internet here, that 1 mile, right, is equals to 1.609 km, right? So probably we can drop out the 9 if you want, and say, man, let me go to 1.6, right? But yeah, that's roughly that. So if you want to convert, like I remember somehow, I'm from Berbice here. We got Berbice people here? Anybody from New
Yes, sir.
Amsterdam?
Yes, sir.
Yes, sir.
Somebody
Yes.
from New Amsterdam, Shondell Bourne said that?
No, I'm not from New Amsterdam. I'm from Friars, Gibraltar.
Oh, okay. Um, okay, yes. But Shondell, I remember long ago we used to right by the bridge, the ferry bridge here. When you're going up the ferry bridge, that's from New Amsterdam to go towards Irish here, right? There was a sign on the ground. I think that time it said that from New Amsterdam to Skeldon, they used to say from New Amsterdam to Corriverton, 50 miles. It was an old sign on the ground. And I remember they replaced it. I think they take the sign out because it was a nice steel structure. It was in the ground, was there since I think I wasn't born yet. Anyway, they uprooted it and they throw it out and they put I think if I remember well, I think they have 70 km there. Is this conversion right? Can somebody multiply and see? 50 by 1.609. See what you get, if I'm correct.
Sir, I got 80.45.
Oh, well, I'm wrong. I think they have 80 km there now. 80. I'm wrong. Yes. So I think this is the sign that is there. Some people must think this is the speed you have to go up the bridge with, right? Because again, there's this big mistake, right? Do you notice all the signs, the Pepsi signs? So there's this Pepsi sign, and at the bottom mark 80 km. I think what they meant is 80 km per hour. That's your speed limit. We can talk about that just now, right? Yes. So I think, yeah, this is what I see on the bridge there. I thought it was 70, but I think it's 80. Okay, you're right. 50 miles from that bridge to Corriverton, right? And 80 km. Well, I think they root out that 50-mile sign, and they now have 80 km there, right? I was joking, not joking. I was telling somebody they're trying to do a highway from here to Skeldon. They're digging up the whole place, and people are living in their cars now. You go in the car, and you take an hour to reach Rosal. You take an hour to come back. You're losing half of your life now in some car. Y'all who are living in Georgetown and in its environments and so working there, y'all realize how much time of your life now you're losing to travel time, right? People don't think that, but you waste so much time. You get so frustrated, right? All of that affects your health and well-being, right? Happy had That's the name of the course, right? All of these things really affect us. You're late more to work now. You lose more. What do you call it? You lose or the company loses more man hours from you because you're late very often, right? Sometimes because you have to travel home now, you lose learning time or instruction time, right? Why? Because of what's happening on the road. I was telling somebody, Sean, you see they're digging up the whole place and they're trying to do drains and so. They took the entire of 2025 and they have not been able to complete, let's say 1 mile you see me and I can't get away from the mile. They have not been able to complete 1 mile of the highway. If you went up maybe 35 where they're doing a piece of the road there, I think they have two areas dug up. 1 mile by 35, and I think more up 6 or something. They have another mile dug up. The entire of 2025, they have only done the drains. They haven't finished the drains. Now, if we are dealing with 50 miles, right? And they only, as I said, they ain't done 1 mile, but let me just give them that they finished 1 mile of the highway in 2025. It means then, right? And they had perfect weather. 2026 hardly had any rain at all, right? The weather was purely dry. So I'm not factoring in rain and so, right? Yeah. 1 second. Yeah. Oh, they want to go now. All right, come. You come finally. All right, go. You smell sweet, man. Oh God, so all of that with me in my recording. Go now. Bye bye. Behave good, right? My grandchildren are leaving, so let us come and give them a kiss and so yeah. So in if they're doing 1 mile a year, it means therefore that this highway will not finish in the next 50 years. Right? Correct me and tell me if I'm talking stupidness, right?
So how about if we use the motion, the force technique that we used in the previous class, where it would cause more force or it'd be harder to start, but as the we go into 2026, all the hard part done. There's a free flow.
Well,
Possible.
where now? With the rain coming? You all see what the weather is changing, right? With the rain coming, we're gonna go faster.
I was just about to say that.
And they finished the hard part because it dig up in front
Yes.
of
All right,
Irish too.
good. All right, good. My grand had to call now. Yes, bye bye. Yes, bye bye. Yeah, all right, good. The grandson and granddad to leave, you know. Yes, yes, it's not getting easier, right? And it's not like, well, right now I think they're bringing people from Bangladesh. If you all hear, Gaisuku is bringing 200. I have a friend who fulfilled the contract. My nephew actually built the beds, and I have a friend who he's supplying the mattresses. 200 beds. They're bringing 200 Bangladeshi workers because Ghanaian workers. You understand? Ghanaian workers. So they're bringing them to help with that is Gaisuku. They're going to work with Gaisuku because they ain't got people to cut the cane and whatever else they're doing with the cane. They don't have people, so they're bringing them. Right? Well, you know the Chinese bring their own people to make the thing. The Indians bring their own people to build that highway from Ogle to Eccles or wherever, right? The people smart, the people give us a loan. Listen to this, you know, a lot of people think that I think I'm gonna edit all of this out before for political reasons. Yeah. People
Give me
think
the
that
loan and then we got paid them back with interest plus we got paid them to do the work.
exactly. So the people smart, right? And a lot of people think that all that is being done in Guyana is done with oil money, you know, and they are so mistaken, right? The gas to shore project they're doing, they borrowed billions to do it. And if you realize it's giving you so much trouble now, the technical part of it, right? We didn't anticipate the technical difficulties to do it because of the kind of soil and where they locate the thing and so. So we're bleeding billions and we borrow that money, right? The bridge we borrowed the money to build it, that Demerara Bridge that they named after somebody. The highway from Ogle to Eccles or what, that was an Indian loan from India. And the people said, no, if we lend you all this money, or we have to build it. And they build it with their own people. And so we got to pay them back, and they don't carry all the money. They give us the money and take back all the money. And we still got to pay them money. Right? So people don't understand those things, Right? Nobody don't understand those things. Like I was telling a person, right? If you're building a highway from Skeldon, I think I said this in a class. You're building a highway from Skeldon to New Amsterdam. And if you're doing 1 mile a year, dig up 1 mile a man. No, they dig up the side, they dig up there, they dig up Palmyra, they dig up number 2, they dig up right now they're blocking up Kanji, now they're digging up the Torrens. So we're digging the whole country up. So what happens now is people say, why are you doing that? But it's politics, because if you say, man, I'm building a highway from Skeldon to New Amsterdam, we don't know about the highway, because if it's at Skeldon alone, we say, man, what means see no highway, right? So here what they're doing, dig up all over. So everybody can say, you don't see what happening here, man, digging up here, man, making it. You got Firish, they dig up Firish, right? You got 10, they dig up 10. You got 35, they dig up 35. So they make sure a strategic location, dig up the whole place. So you can never say nothing ain't happening. Man say, what you talking about, boy? You see the man dig up a whole 35? You see the man dig up the whole Kanji Torrent? You see the man dig up the whole Palmyra Torrent? You see the man dig up the whole Seawell Torrent? The idea is to give people the impression that stuff is happening. You understand? But the other side of it is that look what's happening to our, our transportation system. Did I tell you all 2 of them crash up on the road here? Thankfully, they're not dead. They're critical. Right? So yeah, I'll say a prayer for them. Let them survive this weekend. Yeah, back to this whole thing. So we're looking at approximately, somebody say accelerate. We will get acceleration. Right? So not 50 years. How much you want to give it by? How much with the acceleration you have in mind? I project 50 years. How much you projecting with the acceleration you're talking about? I know what you're talking about, but you must know. How many years you give them? The boy who said we go get acceleration, how much years you were predicting? Like he gone or what? He's not with us. All right. Okay, good. So did we get, what about the other way around? Could somebody Google it? So 1 km is how many miles? I think we had 1 mile is equal to 1.609 km. What about the other way around? That's a rough something. Because as you said,
0.62.
62 miles. All right, good, yes. Right, so at least you have a conversion factor that you can use. If you have to change a certain amount of km, 2,000 km, you have to change that to miles. You quickly, you divide by that, right? If you want the other way around, right, you get 10 miles, and you want to change that to km, you multiply by the 1.609, right? I'm just saying, right? You got to get those things. If you can memorize it, it's very good, So you don't have to always be like today. You wouldn't believe me. The entire morning was going fine, and I had a interview where I was interviewing somebody, myself and the rest of the university. We had to get some new staff, and I was supposed to join at 11:40. Guess what happened at 11:35? The whole internet and network. No, it wasn't. Well, thankfully, it wasn't blackout. We had blackout. We had current, but the internet went down.
Act up.
Yes. No, the act up. There was no internet, and even I have a mobile data plan my workplace gave me. Right? Nothing. Everything. You couldn't even make a phone call. So just imagine, I had another meeting.
Keep this thing in mind. I just want to keep these things in mind when we have exams, right? That they do happen.
Yeah. I know. What could I say? We aren't ready for online education, anyways, right? Um, yeah. So this thing happened like that. Imagine I couldn't get. I didn't attend another meeting because I told them I have this other meeting. So people say, "Watch me," because my other bosses will tell them that I didn't see Gandhi in the meeting. But I have to tell them that the entire thing went down. Everything went down. You know. So that's the nature of this country and place. You know, we can't do a lot of things here because of we still get in blackouts like twice a day, thrice a day, uh, that sort of thing. You know, it's a reason why I got vexed. My daughter used to have some internet trouble, and I bought what's the name? Um, Starlink, right? And then somebody who play wicked now, somebody got friends in the government and said, "Yeah, y'all didn't see what go." I talk about from GT&T. Y'all didn't see Starlink taking over our business. They call up their government friends and they make it a law now that you have to get you have to register or have a license to have Starlink. And guess how long the license take to get? Anybody can guess? How long you take to get a license for Starlink?
A year?
Well, not so bad. 2
3
months.
months. Okay.
2 months. 2 months. You know how long is this? You know what could be done in 2 months? Right? Fortunately, I brought mine before this happened. It was recently I found out that when you bring a thing in, you cannot clear it from DHL. You have to go and fill up a form, lodge it there, pay. I think you have to pay some money, and then, but it's clearly somebody who in GT&T who got some political connections. Say, hey, two things. Yeah, they're messing us. They're messing up our business, and secondly, y'all can make some money because you know if you want it fast, you gonna gotta pay somebody, right? You gotta say, hey, oh, buddy, enable it 2 months.
Sir, so basically, if they benefited from it, you can't get it.
Exactly. Right,
Land of many waters and links.
Yes, links. Yeah, so that's what's going on, right? Yeah, I see my friend come back that was talking about the fifth. I said 50 years. He said acceleration. So I know what will happen if we can do it in 40. But I'll be dead by then. I can't live on with my health and what's going on. I don't see myself living, not even for me. I don't see myself living more than I say 15, 20 years more, right? So I'm not gonna see the highway. I'm gonna die. My grandchildren will just kiss goodbye. They may see it in their older years, right? And let me tell you, it's coming at a terrible cost to us. Because I live in Palmyra. You believe that the dust from that Palmyra city, that they call it, broke down everybody's gutter along the Palmyra Road. Broke. I can't believe. I say, well, how you mean the dust broke down all the man gutter? Dust get the kind of sand that is flying is such that when the water catch it, it doesn't run off into the gutter. It settles and become heavy. And there's a big businessman, Bagjai, who does this distribution of drinks and gas and so on. His entire house sitting just break down just like that. Causing a man about nearly, well, I would think about $500,000 to fix back. Anyway, good. Let me go back to kinematics, right? Oh, that is a word that I think I used in the notes, right? Kinematics, right? And what is it? This part mathematics of kine means motion, right? Comes from that word kinetic, right? So the mathematics of motion. That's what it is, right? Motion mathematics or the mathematics of motion, right? That's what we're going to deal with in motion in one direction or kinematics in one direction, right? So we have to be introduced to some more terms. We just talked about, what did we talk about? We talked about distance, and then we talked about displacement, right? So we have to talk about some other things. We have to talk about something called velocity. Velocity, right? Velocity. You will hear the word. It's related to something called speed as well, right? velocity and speed. And the two of them differ again, right? The two of them differ again in that speed, usually when you talk about speed, you're talking about speed is equals to total distance traveled over total time taken, right? Time taken. And very often, because remember speed and is related to distance. And as we said, distance doesn't take into account direction, right? Like you might be going this way, then you go that way, you go that way. So the distance from here to here, if you measure along the path, you change direction all the time. So you don't respect direction, right? So speed is going to be a scalar quantity. Remember, it's our scalar. Scalar only is concerned with magnitude only, no direction. Speed is going to be a scalar quantity because it's dependent on distance, which is also a scalar quantity, right? And very often you will see instead of speed, you'll say average speed. And why they add in this thing average here is because, well, the distance here changed direction so much. So it doesn't give me an average, an average speed, right? The reason why, let me talk about velocity. You'll see what I'm talking about. Velocity is defined as displacement over time, right? And I mean, you can probably, if you want to qualify it, probably talk about the change of displacement, right? The change of displacement or the displacement divided by the time taken. Now notice that velocity depends on a scalar quantity. So velocity is a, what did I say? Displacement is a scale. What am I saying? Displacement is a vector quantity. Therefore, velocity is also going to be a vector quantity because it depends on direction, right? It depends on direction. So while, all right, when you calculate the average speed, you measure the distance along here. If you're doing the velocity, you actually have to find the displacement from point A here to point B, this displacement, divided by the time taken, right? Because velocity will carry that thought of direction. It takes into account direction, right? Now, again, you'll also hear of average velocity too, right? The reason why is that this idea of drawing a straight line from point A to point B it's not realistic, right? So again, you talk about average velocity and it's usually they take it as okay, they kind of use these two interchangeably, right? They're basically saying, man, the average velocity is well, let me not say that. If you are dealing with a straight line, if you're moving in a straight line, so there's no change in direction, then these two will mean the same thing. So your displacement is going to be your distance and your average velocity will be your average speed, right? There is a related term called instantaneous velocity, right? Instantaneous velocity. Because you know that in traveling along the road, those of you who drive or ride, right? What happens? The speed you're moving at here, is always varying. It's always varying, right? So your instantaneous velocity is the velocity you're traveling with at this instant in time. At this instant in time. And if that changes, very few of us can actually maintain a constant velocity all the time. right? So your instantaneous velocity changes with the condition on the road. So even though you're going in a straight line, your velocity here might be different from your velocity there, might be different from your velocity there, it might be different from your velocity there. Sorry. So what we might very well talk about is what we call the average velocity, right? We take the total displacement or distance, because we're dealing with one direction, and divide it by the total time. And that's what we're calling our average velocity. Right? So average speed, average velocity, these are more practical. These are more practical quantities that you can use more, right? I mean, if you go into mechanics some more and you need instantaneous velocity, you are going to have some what you call calculus. You have calculus tools now to help you determine that, right? And this course is not for that, right? Later on, you might very well go thing, right? And just talking about velocity, I remember. let me go to an example, and I'll borrow. And I mentioned calculus. So you're traveling, like Shondell says, she's from Paris, so she's driving from New Amsterdam to, all right, she said Irish, right? And let's say from New Amsterdam to Irish is about what, 15 km? You think so, Shondell? Or that's too much?
Sir, I honestly don't know his living tongue. You ask where I'm from.
Oh gosh, technical, yeah. All right, yeah. All right, let me just say 15 km, right? And let us say the speed limit from New Amsterdam to Fire, I'm just saying, right, is 80 km per hour. Now, as I said, when you see a police, what do? You slow down. When the police is not on the road, you speed up. So you say, well, nobody can catch me. So here what the people could do now, they put a camera somewhere in New Amsterdam. So they take out Shondell driving. And Shondell, when they catch it in the camera, she's doing a very slow speed, but they take the time. So at 9 a.m., she leaves New Amsterdam. And when the camera takes you out, she's doing nice speed, man. She's doing 50 km per hour, decent girl, right? And then there's another camera somewhere in Firish. And maybe the camera now catches her at, you see something? Let me just do a calculation quick. 15, I said. And they catch her in fire. I think this is all right. They catch her in Firish at 9:15, right? All right. Let me I use 80 here. Well, with the traffic now, you can't do this. You can't go from here to here in 50 minutes. You take about half hour or 45 minutes now. Yeah, all right. Let me say 9:10. 9:10, right? So when you check the average, right? When you check the average, what will you get? What's our average speed over that 15 km? Anybody can say? So the time she took is 10 minutes, right? 10 minutes, which is equals to 0.16. All right. Let me go with 167 hours, right? So her average speed equals to what is that? 15 km over 0.167 hour. Am I being unreasonable here? Should I go with the 15 minutes back? All right, let me go with this. It's what?
$89.82.
All right.
Is it
So
15 divided by 0.167, right?
yes. So you get
Yeah.
89 point something, right? All right, 89 km per hour. Right? So here, her average speed is that. And Shondell can argue that, man, you know what? That me never clock the speed. She can argue and say, man, no, my average speed, hold on. I didn't never think, well, there's a theorem in calculus called the intermediate value theorem, IVT. And the theorem basically says this. I spread out this writing so much. The theorem says this. So if you were to say, all right, let me say this is your motion graph, right? And you are, as you travel from Amsterdam to wherever, good. And in 15 minutes, you said, or 10 minutes? In the 10 minutes, you covered 15 km, right? So the average, that is if I draw a straight line straight, oh my, this is not a straight line. I have great difficulty drawing on this. All right, let me go back with a simple thing. I want to show you something that there's a theorem in calculus, right? So let me say, all right, let me say this is our motion. So the average is you draw a straight line here, right? You draw a straight line. And the gradient of the straight line will be 15 over 10, right? The gradient. So that's our average speed, So there's a theorem that says that the gradient of this curve at some point is going to be equal to this average speed. So our average speed is 89 km, right? So somewhere on this curve, the gradient is also 89, which means that she was speeding at 89. There's a theorem like that in calculus. So she can argue how much she wants, but no way. I didn't do no 89. No. The average is telling you that you did speed, right? And the intermediate value theorem is telling you that somewhere along this curve, the gradient is also 89. And by the way, right? I'm only talking like it's fun, right? But in foreign countries, they actually send you they charge you, saying that you were speeding, right? So they'll take two positions that you're driving on a route, right? And they take when you are here and when you are there, and they're not interested in your speed. Sometimes you fool like how you know the camera there, so you slow down. And as soon as you pass the camera, you can't 90, 100, right? And if the speed limit between here and here, point A and point B, is 80, and they found that your average is 89, well then at some point along here, you were doing 89. It could be you were doing, some parts you were doing less, some parts you were doing more. But one of the times, you were doing 89, according to that theorem. And they send you a ticket. That's proven science, right? They send you a ticket and it's proven science, they charge you. I don't know if you ever heard of that. Yeah. So back to we talk about displacement, we talk about velocity, we talk about average velocity, average speed. And he said when we are dealing with motion on a straight line, when the motion happens in a straight line, you could use these words interchangeably. Distance and displacement can be used interchangeably because you haven't changed any direction, right? So distance on a straight line or distance in one direction is the same as a displacement. Same thing, average speed and average displacement will carry the same thought if you're dealing with one single direction. Of course, you can talk about motion in a straight line, but you change direction. You go in a straight line and then you go like that. So two straight lines, but you change direction. So in this case, velocity, average speed will mean two different things, right? Will mean two different things. Good. Let's talk a little about the units that will be used. The common units that we use, whether be it we're talking about speed or displacement, right, will be km per hour, right? You also hear of meter per second, right? You also hear about meter per second. And then, as we said, we just do not, no matter what, we can't get rid of miles per hour, right? So we're dealing with km per hour, meter per second, miles per hour, right? When we're dealing with the movement of a vehicle, oftentimes this is what you're dealing with, right? This here, if you're dealing with shorter distances, shorter time frames, this one is important, right? Like maybe you're talking about Usain. What speed does he run? I'll give you a story with Usain just now, right? We might use meters per second because I think he runs faster than 10 meters per second. He runs 100 meters in less than 10 seconds, right? So he runs greater than 10 meters per second. If we had trains in this country, we could talk about km per minute, right? But we don't have trains, right? But we do hear people still talking about miles per hour. Maybe a very old vehicle would still have miles per hour on the dashboard. You know, that little what do you call it? The speedometer, right? It would usually tell you the speed you're moving at, right? In and that speedometer on your dashboard, right? If you're a driver, that is what tells you your instantaneous velocity, you know, right? But how you can't really use that in doing calculation for a whole journey, right? You have to use the average velocity or the average speed, right? Which is a more useful quantity. What you use that for on your dashboard there is to, make sure you are within the speed limit and so. And again, now that we're talking about, well-being and safety and so, right? These are important things, right? Look, all this construction on the road. Even though we have, okay, the thing says 80 km per hour. Does it mean we have to travel at this speed? Does it mean we have to travel at that speed?
No, there's the maximum speed you could travel without getting a ticket.
Very good. Yes. Right? As the maximum speed you can travel. You can be traveling a much less than that, but you're driving dangerously, you're overtaking recklessly, you're undertaking, you're going in the path of others, right? So you don't have to wait for 80 for get in trouble, right? Yeah, so 80, even though the road says 80, right? You have to understand a lot of other things. That might be your right, but there are times when you have to look at the bigger picture, right? Some of you see, okay, you see children on the road, right? What you do, even though it's your right to drive 80, you drive 80 and knock down one of them, and then you got to spend some time in the jail, you're going to be all right, right? So even though that's your right, you have to keep in mind that, well, there's so many other factors. Rainfall, you're going to do 80, so you have to think about safety, right? Some of you, anybody here driving one of these trucks that is involved in all this construction and industry in our country? Anybody's a truck driver in this class? Do you work with those people? Maybe you're a supervisor or you your business or the industry you're working with employs truck drivers? Anybody works with like that Banks DIH, DDL, Ansel McCall, Buster? Anybody works with these companies? Nobody? I'll tell you what, some mornings I go into work, right? And these trucks are laden with tons of drinks on it and whatever other things they're selling. And sometimes I'm driving near on the 19 road, I'm near this. And those trucks would pass me, I know they're doing about 100. Because if I ever attempt to overtake somebody with this, you can't be doing 80, you got to be doing 90 to 100 to overtake somebody with 80, because you got to overtake them, make some distance, and then cut in front of them. The trucks are doing 100, right? And those are 25, 30 tons because not just the truck, you're thinking of the weight on the truck. These men, I want to know what's wrong with them, right? No consideration to none of the rules of the road and safety and nothing, life, nothing.
Sir,
So yeah,
so right now again, New Sandpit opening lane, then them trucks is going down like it's 4-door pickup.
yeah. Yeah, if one of you, I don't know what areas you work, you know, and have some influence, like I was suggesting a curfew, right? Where like in the morning, Chandel, if you were ever to come to Borbees, right? The traffic has gotten from Fire to New Amsterdam in the morning, takes about little more than an hour. I am not joking. From the time
Yes,
you hit
sir.
Palmyra Road, yeah,
We have
you
a well, a regional office up there that I usually visit, and we take like 1.5 hours to reach where we were going.
yes, if you got to go from here to, let's say, UG, right? I live in Palmyra. When you see a hit Belvedere, Fire Ridge Belvedere area, you take more than an hour to reach UG. So when I go to work now, we have a 10 o'clock meeting, 8:30, I got to go on the road because I wouldn't reach in time. Right? It take a little more than an hour now to reach from Palmyra to UG, which long ago, 20 minutes. So I was suggesting, I said, man, whoever, and one thing, there's nobody you can talk with these days. A curfew, 7:30 to 8:30, no trucks on the road. They should park or they let them load up during that time or take their breakfast during the time. Same thing with the afternoon school over to 2:30, from 2:30 to 3:30, no trucks on the road. It wouldn't make the road billing, as somebody said, I said 50 years, it wouldn't take it to 60 years. No.
Sir, but you remember we had a countrywide curfew as it relates to those big trucks that they used to travel from 6 in the afternoon to 6 in the morning.
Oh,
They do,
Barbies
but
is
it,
not part of Guyana, where you, Chanel, every rule but tint and trucks and all the rules that you hear about on the news. First of all, what a guy named Juan Egil, he's involved in theater. Right? He likes to go out and all the trucks are rubber, pull them away, block them all. That's theater, right? He knows nothing what that goes on here, right? So that countrywide means George, though. Nothing goes on or nobody enforces anything in Bordeaux, right? So yeah. So the safety of it, I mean, I wish if somebody had the influence to change some of that with these trucks and so on. Imagine these trucks would work 24 hours. Nighttime you hear them all up and down. I said, wait, these men, they ain't got wives. Man, look, let me not get into that. Yeah. All right. Good. Let's talk a little about converting one to the other, right? I think we still need to know how to convert one to the other. So maybe let's look at maybe an example or so, right? And we need to know, all right, let's have a converting units of speed, right? Converting units of, I'll go with speed slash velocity, right? Remember, when you talk about velocity, you simply mean speed in a particular direction, right? So we know the connection. 1 km is 1,000 meters. We know that. All right, we might need 1 hour equal 3,600 seconds, because we can convert from km per hour to meter per second. And then the one with mile, right? 1 mile equal 1.609. I think somebody gave us another one earlier. Good. So let's do some examples. Let's see. We can convert. All right. Let's say we want to convert 25 meter per second to. Oh no. Let me use Usain thing, man. Usain runs at. Wait. I gotta tell you all this story with Usain just now. 10 meter per second to km per hour. Compare it with a car. So how much will that be? What do you do? So we got, let me just, so this is what you can do, right? You put 25 meter per second, right? And this is a shortcut, like you multiply it by 1 km, right? 1 km is, what is it you call it? 1 km is 1 km over 1,000 meters, right? And then to convert seconds to hour, you will multiply, okay, by 3,600 over 1, right? So, okay, seconds over hour. Is that too much work? So what I'm doing here is getting rid of, we're getting rid of the units, right? So you will end up with km per hour. Notice what? This meter will cancel with this meter. This second will cancel with that second. And you end up with 25 multiplied by 3,600 over 1,000, right? Which will be 25 multiplied by 3.6, right? km per hour, which is, you can give me a number. Of course, you can see the
90 km per
shortcut.
hour.
How much?
90.
Oh my mama. So Usain is running at this speed, you got to be charged. Usain is running at that. No, oh man, I didn't go with 10. Wasn't 10 here? 10. Oh my. Y'all didn't remind me.
You
Oh,
put in it 25 rather than the 10.
10. Oh gosh. Yeah. I started with 25, and that's why. Let's go with 10. 10. I have to put 10 here too. That's saying Usain can't be running so fast. Something wrong.
36.
36, sir.
Okay, 36, yeah. 36 km per hour. Right? And that's pretty fast. Right? He could outrun most cars that there on the Palmera Road here, because we can't drive the speed now with the digging up that's going on. Right? Yeah. So a shortcut, right? To convert from meter per second to km per hour. I only did this to show you what's happening with the units. All you need to do is multiply by 3.6. Right? So is that easy? Let me move up this whole thing.
No, sir.
So convert from meter per second to km per hour. Multiply by 3.6, right? From km per hour to meter per second, what do? divide by 3.6. Nice shortcut, right? Nice shortcut. Then do one that involve km per hour to miles per hour, right? Because we still, as I said, we are shackled to the British system, and you still have, I would think the older cars still got miles per hour. Nowadays, I think all the cars that come from Japan got km per hour. As I said, they routed out the sign by the ferry bridge, the Kanji Bridge, right? So let's say you're changing, all right. What is it? Let's go with, all right, 100 km per hour. I'm using some nice numbers. To convert miles per hour, right? That's what they're right. So notice that the time is the same, right? Hour. So all you got to really do here is change the what do you call it? The numerator, right? The km. So 100 km per hour multiplied by 1 mile over 1.609 km, right? And this is like 1 then, a fraction of 1. It's like you're multiplying this thing by a fraction of 1 because 1 mile is the same as 1.609 km, right? And you get what? So you get 100 divided by 1.609 miles per hour, right? Whatever this is. How much is it?
62.15.
62 point.
Point one.
0.15.
All right, 62.2 miles per hour, right? Roughly. You can even drop that fourth decimal in. 62 miles per hour, roughly, right? So you can see it clearly there, right? To change from, I need not do another example. To change from km to mph, you divide by 1.609. And to convert from miles per hour to km per hour, you do what?
Multiply.
You multiply by 1.609, right? That shouldn't be hard. I have a little chart here. I'm going to cut it and bring it over. How do I cut that? Give me a second. It's not allowing me to. All right, let me cut it. Copy. Paste. Right, so you can always, this is a nice little table you can use, to go from one to the other. You got it? I can move this. It's a helpful little table, if you can remember the numbers. multiply by 3.6, divide by 3.6. The next one has to do it multiplying by 1.6. The other one is divide by 1.6. All right? If you can remember that. A nice quick reference, like rather than having to do that thing with the dimensions and have them cancel out. And so that's for the scientists, right? And one of the things I want you to always remember, it's this matter of speed limits, right? Observe them. And as the one student just point out, not because it says 80 mean you gotta drive 80, right? You have to consider so many factors: the conditions of the road, the condition of your vehicle, your impulses. Did you rest well last night? Are you fatigued? Are you maybe stressed? You had some trouble at home. You use drugs, and I don't mean illegal drugs, illegal one included, but maybe you drank something for a headache, that sort of thing. All of those things you want to consider, because driving is so much more. The conditions of the road, rain can fall, place muddy, there's construction on the road. So it's not as simple as, the numbers, 80. So by you're doing good, but you're driving at 50. Where you going? Funeral? That it's not about that, right? You want to think, because let me tell you something. Stuff that you do in a second could change your life forever, right? And I guess you all know that, right? You could make a split-second decision, and you do something stupid, and it changes your life. It changes the life of others. Oh, sadly, I just received, I didn't know, I saw it on the news. There was a man and his daughter in an accident, and both of them died. Anybody knows about that?
Yes, sir, in Essequibo. It's 3 persons was on the motorbike. But listen, it goes two ways. The truck wasn't supposed to do a U-turn on a major road. And the speed that he was coming in, because the other vehicles stopped for the truck do the U-turn. But like the motorbike man think like he could bypass the truck before it turned fully, and it crashed into the front part based on the video that I see. And the baby died, and I ain't even seen the man foot on the body, and the lady they say critical.
Oh, because the lady works with us at Eugene. She's some kind of security manager. I don't know if it's a Turkine or we have a branch somewhere in Essequibo. I don't know, but I was sent a funeral, an email about the funeral and the wake and whatever. And I said, wait, father and daughter, what is this? I remember seeing it in the news, but I didn't know that.
Today? Are you talking about the roundabout accident with the father and daughter who died the other day at going into South there?
Let me glance at let me tell you the person whose it is. Funeral notice. The person name Claudia. The man name Kenneth Johnson, and the child name Kelly Johnson.
They gotta be the roundabout that happened. I think it's sometime
Is the
last week.
roundabout incident?
Yeah, that's a roundabout.
On Thursday, March 5, that last week. Last week, Thursday, this happened.
Yeah, that's a roundabout issue.
Yeah, that's a roundabout.
Oh, well, the wife. What happened there? Could you say? Could you just give me a little bit?
Sir, based on the video, it looks like he was speeding and probably he dropped asleep, because I can't understand how he reached there, and he was speeding based on the video.
So I think it's a straight road. It wasn't a straight road. He must be thinking, he coming because he's live right in South. I don't live far from the roundabout. And in night, I don't believe he know it. And we get a road, right? Like Arby Bark Road.
Yeah.
Into the roundabout. But he must be thinking he could go straight. and he fly over.
Oh gosh. When you fly over, what do you mean
Listen,
fly
if
over?
he
Try
didn't
get people
know
out.
how, I think if he used that same interest to going south, he should have known the way to come out and not with all the speed. But it was that
Yeah, he just fly
situation.
over into a lot.
It could be that he
Somebody
dropped to
vulcanized the
sleep
shop.
too.
Yeah,
Could
you
be
see
that he
all
dropped to
yeah,
sleep.
yeah.
But
But
he
it
come
just
with
goes
too
right
much
back to
speed,
what I'm saying,
He
sir.
right?
was
That
speeding.
Too much speed.
yes. And then sometimes, I mean, we're not judging too, right? Because you never know he was late for work or he had to drop off the daughter to some school and then go to work,
Sir,
right?
that was
And
wee hours in the morning or midnight, something like that.
oh my, oh, it's not morning. All those are decisions, you got to think about, say, well, look, should I be doing this in the night? Look, I got a car, right? My wife and we bought a car, and let me tell you, I hardly drive the car because if she got to go to New Amsterdam and I know it's in the morning, I say, I'm going on the road too crazy, right? Take a public transportation or I call a taxi. Where I would look at the probability of an accident based on what I know on the road, you know. So sometimes you make decisions, and even me, I've made a lot of bad decisions on the road. Um, I did get off, but all in all, I'm trying to say that we need to be careful.
There are some people thinking about the 5Ds instead of the 5Cs.
I lost you all there for a moment. Y'all can hear me,
Yes,
right?
sir.
Yes,
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 sir.
sir, you're back.
Yeah. All right, good. So another quantity that you'll hear about is the quantity acceleration. Acceleration, right? And acceleration, again, you can have what you call instantaneous acceleration and average acceleration, right? So you can have, all right, the average acceleration will be, the change in velocity, average acceleration equal change in velocity over the time taken, right? Time taken. And of course, you can have instantaneous acceleration. Instantaneous acceleration, right? Which is acceleration at an instant, in that you quickly change velocity in a small time frame, right? We're not going to deal so much with instantaneous acceleration. We might mostly deal with average acceleration, and sometimes we don't even use the word average in front there, right? We might be talking loosely about acceleration, and in your mind you're thinking of, well, if there was a change of velocity over a time period, well, we call that the acceleration. But there are times when instantaneous acceleration is something that is important, right? Like I don't know if you all, those of you who are into cars and so, people are very, very, especially if you got to do like you're talking about racing and so, right? People are interested in, can I do an instant acceleration of so much, because takeoff, like the point of takeoff, that's important to them. But for everyday purposes, we are more interested in what we call the average acceleration, right? Like you hear some people say, like, you know what? An average car can move from 0 to maybe 20 in, right? This is km per hour in maybe 5 seconds, right? Yeah, you probably can do better than this, right? You probably can do about 0 to 30, 40 in a 5-second interval, right? Drivers in the class, how do you do it? You would do that? 0 to 30 in about 5 seconds, or you do it faster?
Once we late for work, sir, these
Yeah.
Sir, it
Hear the man?
depends.
You hear? You hear? Yeah, right. And I think that is where these electric cars are coming out. They beat the gasoline cars, right? Because recently they had a race in Kanji here in Borbies. They brought I forgot what kind of race they call it. And the electric car run away and left them because electric cars, you don't have to put nothing in gear and one was. When the electric car start, you didn't even know. And they could move from like 0 to 60. 0 to 60, sometimes more than this, in less than maybe 5 seconds. They could do this. Whereas the other cars, you can't do this. Can't do that. Right? Can't do that. You might barely move from 0 to 30 in the 5. But electric cars, you can quickly accelerate with them. Right? Because they have a motor. It's just a motor spinning. Right? The other one, transmission and all kind of thing comes in the way. Right? Yeah. And acceleration is usually measured in the most common one you hear about is meter per second. You don't hear about very many other units. Sorry, meter per second square, or you write it as, oh, I'm supposed to tell you too, when you come to write in km per hour, and so you can write it like this. Km and the hour with a -1 on top. Meter per second, you can write it like this, right? We can write it like this or like this. You can write it using this index on top there as well. Same thing here too. Meter per second square is acceleration. You can write it as meter per second square like that, right? S with a -2 at the top here. You don't hear of, I mean, if you're into space travel and so, then it's when you talk about km per second, right? Second square, sorry. When it comes to certain acceleration, right? But this is the unit you hear most of the time. And related to this is something called G. Somebody was asking if this means gram the other day. G is acceleration due to gravity, right? G. And it's usually around 9.8. Some people put in a 1 there, meter per second square. Sometimes for ease of calculation, we approximate it to 10 meter per second square. And I'm going to tell you what, this difference you see here, 9.8 and 9 and 10, this difference is very significant for space travel, right? That is why you find a lot of space stations, they want to come towards the equator, because at the equator, acceleration due to gravity is a little lower, right? Whereas in those northern countries, it's a little higher, right? Sometimes in those countries, it can be 9.81. And you see this one here? It makes a difference when you're dealing with, you know, acceleration, right? We're not going to get into it. 10, bad. This is bad. Cost far more fuel and so, right? And the vehicle got to be heavier, because if you got to get more fuel, the spacecraft got to be heavier. You know, the engine got to be more powerful, all of that. And that's why you'll find that they have a space station in French Guiana unto this day. They wanted to put one right in Guyana here, but you know, people, the Guyana government didn't consent and so, right? So it does make a difference. Keep this in mind, because it's going to be very useful. It's going to be very useful later on in our calculations and so, right? Speaking about the mathematics now of motion in a straight line or in one dimension. Well, we're going to look at two things. I don't think we can look at both today. We're going to look at one thing now today. And Tuesday, we'll take up the discussion again. So what we're going to look at is the equations of motion in a straight line. Right? Equations of motion. It's not one, it's equations. Right? And there are a number of them. You'll see V equal U plus AT. Well, you will hear what these mean just now. You will see sometimes they use S, right? And some use X. Right? Some places use X, some textbooks use X. Maybe you want us to use this to get away from S, because S you might think it's speed, right? All right, let me use X too, because X X, you might want to think when you're plotting it on the x-axis, right? You might want to think that, well, let me use the S. And S here doesn't mean speed, right? S is equals to, all right, there's one like this. U plus V over 2, right, times T. Sometimes you write it like this. Half of U plus V T, right? There's one like this. There's another one like this. And there's another one, oh, sorry, not S. V square equal U square plus 2AS. Right? So these are some equations. And what do these symbols mean? U is initial velocity. And remember, we can use the word velocity and speed interchangeably, because when we are dealing with motion in a straight line, the two of them can be used interchangeably, right? V is the final velocity, right? S is the displacement. And again, this can be used interchangeably with distance if you're dealing with motion in one direction. Well, you know what? Oh my, what did I write here? You know what A means? A is acceleration, right? And T, well, that's a no-brainer. Time, right? So whenever you're analyzing a motion, and we wouldn't have the time today to do some examples, what we probably could do is we'll take Tuesday and do some more examples, and so using these equations, right? I'll bring a couple of examples for us to try. So when you're dealing with motion in a straight line, one of the things that can make the analysis of the motion very easy is your use of these equations, right? You might be given a quantity or two, and you have to find another one. So you have to see which equation is best suited, right? Maybe you're given, all right, you're given the initial velocity, you're given the acceleration, you're given the time, and you have to calculate this. Or you're given the final velocity, the initial velocity, the acceleration, you have to calculate time. You know, you would see which one is best suited for the problem that is described. Right? And we're going to do some examples, don't worry. Now, part of, or when we talk about motion in a straight line, a motion that we can analyze using these equations is when something is dropped from a height or projected vertically upwards, and whether it goes up and stays or you know, whatever happens up there, or it comes right down back. These motion equations can be used, right? And they can be adapted, because when we throw something up vertically or we drop something down, right? The acceleration that comes into play is G. The acceleration due to gravity. And very often, for the sake of simplicity, we usually neglect air resistance and so, because that interferes with how the body will accelerate. For simplicity, if you study mechanics and so to a higher level, well, then we'll take in all those things into consideration. But for now, very often when we're dealing with something being thrown up or something being dropped vertically downwards, we will use G as 9.8 or 10, depending on what I say, right? And these equations can now be modified, and you can use them in this form. Let me see if I can take out this now here. So we can now use the equations in form. You don't have to memorize all these equations. Once you remember these, right, try to remember them. So the equations will become V equal U plus, well, depends on how you use G, right? You can replace the A with a G, right? With a G. And depending on how you treat upward motion and downward motion, right? Well, if you treat downwards as positive, lots of times people do this. Let me remove that. People treat downwards as negative and upwards as positive. If that's the case, because G is acting down, right? You will normally modify the equation and say, well, V equal U minus GT. That's if you're treating up as positive and down as negative, right? Because G is always acting down, right? So you will modify the equation. You wouldn't use this. You would use this. Down here, well, this doesn't deal with G at all, this one here. So that's out. This one here, you will use S is equals to UT minus half GT squared, right? Again, you're treating up as positive, down as negative. You can decide that in your problem. You can say, look, I am treating up as negative, down as positive. You can do that, right? Especially when you're dropping something. You're at a height and you drop something, right? Similarly, these are the equations here now. S is equals to VT. You will put a plus there now, half GT squared, right? And the other one is V squared is equals to U squared minus 2GS, right? Where again, down is negative, up is positive, right? So a little modification of your problem, of these equations, will help you with vertical motion. Let's do a simple one that involve, okay, motion in a straight line, when you drop something or when you throw up something. And that will close our class for today. Do a simple one, just to show you how these equations can be used. So let's say you're on top of a building, some building. And all right, let's say the building, well, Guyana is getting high buildings now, yeah? Anybody who works in a high building in Guyana here? Any one of you work in a high building?
Sir, I used to work in a high-ish building.
Which one is that? What building is that?
That was the top floor of Footsteps Mall.
Okay. And that's about, give me an average height.
Ooh. Damn. I don't know, maybe 50 feet. I don't know.
50 feet.
It was about 4 or 5 stories up, so I'm not sure how tall that is.
Let's say it's about 20 meters, right? Let me go 60 meters, 60 feet, 20 meters roughly, right? Good. So let's say you're up there now and you drop something. You drop something from up there and it's falling, right? So you want to know, all right, how far does, all right, let me say, okay, this is the thing here, right? All right, let's say, let me not use far. What will be its speed? Remember, we're using the word speed and velocity a little interchange because it's coming down straight down. No change in direction, right? So the thing, you drop it. Drop it means u equals 0, right? U equals 0 if you want to use meter per second, right? Because you're dropping it, right? What speed will it hit the ground with? And let's say somebody is here, right? Like I said, and let's not consider their height. So the thing falling 20 meters. What will be v when it hits this ground? But we're looking for an equation that involves what? We got u. We don't know v. We have distance, but we don't have time. Can you think of one of those formulas? Which one you think? Oh, we got g, right? We will know g. Let's use g as 10 meters per second square. So the formula might be what? V square is equals to u square plus 2as, right?
Yes, sir.
Good. And we're going to use g as positive here. We're going to use down as positive. So v square will be equal to, well, u square is 0, right? 2 times 10 times the height is 20 meters, right? So v then will be equal to the square root of, what's that, 400?
Sir, 392.4.
Where you get a number from? 2 by 10 by
No.
20?
Oh, I used 9.81. My
So use
400.
10 for, yeah, 20 meters per second. Right? So well, you're all talking about working at a place, some shoe place. You throw down a shoes, right? By the time it hits the ground here, it's going to be traveling at this. The mathematics is a little beyond you. We haven't gone that far, and I don't think your course covers that. But if it goes and hits somebody, right? If it hits somebody and it comes to rest, and I'm saying it hit and doesn't bounce, because bouncing would make it complicated. If that shoe hits someone, let's say the shoe is 1 kilogram, right? Now the shoe in 1 second moves from 20 meters per second to 0 meters per second. And it happens in 1 second. So the deceleration then, right? The deceleration. Oh, deceleration is a negative acceleration then, right? While acceleration is like something going from a slower velocity to a higher velocity. When something goes from a higher velocity to a lower velocity, we say decelerate, right? It slows down. So if that happens,
Yes,
right?
sir.
Well, if that happens, the decelerate, yes.
You can use deceleration in that example because it's the one speed is moving and this deceleration is not slowing down.
No. When it hits the person's head, we are saying that it goes instantaneous deceleration to. It moves from 20 to 0. From 20 meters per second to 0. Hit the person's head. Right? So the deceleration, forgive me for spelling and so, is equals to 20 over 1 second, right? 20 meters per second in 1 second. which is equals to 20 meter per second square. Now there is a formula, and this is beyond your course a little bit. I just want to show you how dangerous it is, because we're talking about safety in this course, and the well-being of others. If the shoe is 1 kilogram, which is about 2 pounds, and some of you guys shoes them weight there, right? So if you throw down a shoe and it decelerates on hitting the person's head in an instant, it decelerates by 20 meters per second. The force that it exerts is going to be 20 by 1, which is 20 newtons, right? 20 newtons. Now, the question is, well, how dangerous is this? ME, yes, 1 by 20. How dangerous is 20 newtons? 20 newtons may not seem like much, but I'm thinking that because it acted in such a short time, the impulse, there's something in impulse, could very well harm that person, right? I mean, 20 newtons. Let me see. It might not crack the person's skull, but it might give him a terrible
Concussion.
yeah, maybe a concussion. They got some internal hemorrhaging or something, right? I'm just showing you, something like the simple as this. 20, it's traveling with that, it comes to rest. It means it delivers all that force to this person's head. So it's about 20 newtons on the person's head, right? That's a lot. It can very well cause, a little problem. In this problem, notice we treated coming down as positive. So we use G as positive, right? We use everything as positive. But if you throw up something, right? You might very well want to treat up as positive and down as negative. And maybe we can take, let's take one like that before we close. Let's take a problem where, okay, you throw up something. Oh my, look at my straight line. Oh gosh. Somebody here said they were working with President Garrett.
Sir?
Somebody did say that. When y'all do like these flag salutes and you shoot, I don't know if the guy is here. Do you use blacks just to get it sound? Or do you use real bullets that actually shoot out a projectile? Is the guy in the class?
Don't think so, sir.
Yeah, I hope they're not using projectiles, because if they shoot out a bullet, right? You would find that, okay, all right, let me go with that bullet example. I wonder when you watch the video, if you shoot up a bullet and the bullet goes up, and let's say it goes up with 200 meters per second, that's a lot of speed, right? It will go to a certain maximum height, right? And we're not saying they shoot it like at an angle, right? They shoot it up. And it's coming down back. What speed will it come down back? And again, if it hits somebody and virtually come to rest, well, whether the person can die, let's analyze that. So it goes up with that, right? Let's ask some questions. What is the greatest height that the bullet is going to reach? I'm not going to write out all the words, right? Maybe, okay. What speed will it hit the ground with? The ground with, right? ground width on coming down. I'm writing very good. So initial speed, 200 meters per second. You want to know what's the greatest height. Now, so U equal 200 meters per second. Or we can treat up as positive, down as negative, right? So when it reaches the greatest height, have you ever thrown something up? A ball? I remember when I used to teach at high school. The school was fairly high. And they have some students sometimes who throw up a ball. And when I'm on the top floor, the ball would virtually come in front of me that I could stretch out my hand and catch it. But when it comes to its highest point, it comes to a stop. You ever see that? So at its highest point, V is equals to 0. When the ball this bullet, when it goes right up to the highest point, it stops. Right? Because what's happening is the Earth's gravitational pull is slowing this bullet up, right? So when you shoot it up, it starts off with this, but it starts to slow till it reaches highest point, and then it will fall down back, right? So, so U is 200, V is 0, G we're going to use as minus, let me go with 10, right? 10 meters per second squared. So we need S, right? Height. So we can say what? S is equals to UT, what was it? Minus half GT squared. We want to go with that. So it's going to be equal to 200. No, we don't have T. Oh gosh, we don't have T. So we can't use this equation. What's going on there? We don't have T. All right. Which equation doesn't have T, but can still give us this information? Let me go with V square is equals to U square plus 2AS. This one look right? So V is 0. U is 200 square. U is 200 and we square it. Plus 2 times minus 10 times S. So S then is equals to, let me put it like this. This is 2 by minus 10 is minus 20, right, by S. When you bring it over here, you get 20S equal to 200 square, how much? How much? 2, 3.
40,000.
40,000, right? So S then is equals to 40,000 over 20. Oh, that doesn't sound right. 2. Okay, that is a great height. 40,000 divided by 20. I think my bullet is it's too fast. So that will go with that. How much is this? 4,000 divided by 2 is 2,000 meters. 2,000 meters. That's your greatest height. Now the question I want, and that's why I was asking the boy, if they shoot blanks or they shoot a real bullet that has a projectile inside. When this thing goes right up and comes down back, what speed will it hit the ground?
Sir, it's saying that the speed is 20. You get 20S. So
200, that's 200.
Pardon?
200, it's 200, not 20.
Oh, 200.
It's 200, yeah. By symmetry, it's going to hit the ground with, what will happen is that you're going to come down back and you're going to hit the ground with that same speed. Remember here we are taking out air resistance and so on, right? Because of air resistance, it's going to come down with a little less speed, right? However, that's a lot of speed for a bullet to fall down back. If it hits somebody, it can harm them, it could kill them, just like a real bullet. because if we were to go now and look back at this equation, right? If we were to go back here, right? So we're going with v squared equal u squared plus 2as. We know the distance, right? If I'm to go back now, v squared is equals to, remember, from the highest point, u is 0. So it's going to be 2 times 10, if I'm to consider down as positive, right? 2 by 10 by, it dropped 2,000 meters, right? So no need to put in it. So v then will be equal to the square root of 2 by 10 by 2,000. And that will give you back your 200 meter per second. Right? So that bullet will fall down back with that exact speed. And why I'm asking if the guy is here, because if they're using real bullets, when that bullet is coming down, you better look out. And even if they shoot it at an angle, whoever is here can very well be harmed. So that's why I'm saying, I think, and maybe I have to ask him, he would know better. I guess if he's in the next class, he will tell us. If he watched the video, of course. Because if they use blanks, what the blanks will do is that the blanks doesn't have a projectile. Let me explain what I mean. The guy might very well correct me, because from what I know, the bullet is shaped like something like this, right? And the projectile is kind of inside here, right? Inside here. So the back here would have gunpowder. So when the hammer hits here and there's an explosion in there, the shell pitches out the gun, falls on the ground, the empty shell. And this little piece of metal here is what shoots out and hits you, right? So what they're doing blanks, they wouldn't have this. They just have nothing there, right? And that's what they do a lot in the movies and when they're starting races and so, they'd have a blank. So when they shoot it, you hear the song, same song, but nothing comes out, just a little smoke, and the shell falls on the ground. Right? So you hear the song because that's what you want. You want to hear pow! But no projectile goes out to harm anybody. And that's what I'm saying in this problem. At least theoretically, the bullet is going to come down back with 200 meters per second.
Good night, sir.
Yeah. All right, good. So I know, yeah, it's our time, right? Yeah, so we'll stop there. We'll stop there, right? All right, good. We see each other on Tuesday.